Hello, everybody. Hope you all had a good weekend. So just to orient you on what we're going to go over this week, last week we were talking about micelle or surfactants and micelles. So we have an understanding of what surfactants are, how they can assemble into certain structures like micelles. And also we talked briefly about different types of effects surfactants can have uh, on solutions or the properties of water. So we've already known that they can reduce surface tension, but we also learned that they can actually stabilize certain structures like thin liquid films, for example, which is the reason why we can make bubbles using dilute solutions of surfactants. So we're going to be continuing along there, building up a little bit in complexity as we go on, and also moving towards some practical applications as well as some more advanced things. So today we're going to talk about emulsions. On Wednesday, we're going to be talking about coatings, so different types of coatings. So some of this will be tied to emulsions and micelles, and some of it won't. This encompasses a lot of what we talk about in this class, so I think it's a good time to fit it in. Friday, we were scheduled to have a quiz, so I'm going to have that be a take-home assignment. So on Friday, we're going to go over a paper that talks about some of these concepts, and your quiz will be over the weekend to answer some questions about it. Okay, so that will be the goal, and I'll post an announcement just to make that clear to everybody so everyone's on the same page. Last thing that I should mention is everyone in 408 should have gotten feedback by now on their initial phase of the project. So again, the goal of this is not to be punitive. So if you fell short of what the expectations are, I'm giving everybody the chance to catch up and make sure that we're all on the same page. So the goal here is to make sure that everyone is set up for succeeding in this final project and fulfilling all the expectations. So so a lot of you did it just fine, so your feedback said that, but in some cases you or your group may have gotten some feedback in what you should improve, so you can get full credit and also be prepared to do well on the final project. Okay, so let's move forward and make sure my chat window is open. Okay, so before we talked about micelles. So if you remember, micelles are assemblies of surfactants. So for example, if you have water, and you have a bunch of surfactants, and you're beyond the critical micelle concentration, you will have some assembly in 3 dimensions like this. So basically, these polar heads, which are much more energetically favorable to be exposed to water, will go to the outside, and all the hydrophobic tails, which do not like to be exposed to water because of hydrophobic interactions, sort of group together. And this is thermodynamically favorable, so this happens. So there's a couple aspects of this that we should cover. So this is what happens if we put surfactants in water, and when it's above the critical, the concentration is above what we call the critical micelle concentration. CMC, that's a little recursive, huh? The concentration is greater than the critical micelle concentration. But what if we put surfactants in some other phase like oil? So in this case, the hydrophobic heads would not want to interact with the oil, and the hydrophobic tails would chemically be very much like the oil, and you would see the opposite sort of structure take place, where these heads group together. Okay. Likewise, the surfactants on the surface would assemble like this, right, with head up. So all of these these phenomena can be experimentally verifiable. So you can actually do experiments to show that this happens. Okay, so another thing about that's important about micelles is they increase solubilization. They can increase the solubility of otherwise sparingly soluble substances. So for example, in the left image right here, inside of this micelle structure, if you were to add oil and agitate it, oil would be attracted inside of that structure. Likewise, if you were to add water, water would be attracted to that type of structure. So when you start forming these sort of superstructures where you have, again, let's say water here, and suppose you add oil and surfactants and you mix it up, what you can get are structures that can encase droplets of oil. Let's see. And this is called, in this case, this will be an oil in water emulsion. So you can have the opposite. In the right case, if you were to add water and you were to agitate this, this would be water in oil emulsion. So again, when we talk about foods, for example, if you've ever made like salad dressing, like a vinaigrette, where you add usually oil and water and some other type of surfactant. Typically, that might be something like, I think, oftentimes you'll use like mustard or something, which acts as a surfactant. That is oil and water emulsion. So the other thing that you may be familiar with food-wise are things like mayonnaise. Does someone have something to say? Okay, maybe that was just a mistake. Okay, and mayonnaise is a water and oil emulsion where you start with a continuous phase of oil and there is some amount of water in there. So things to think about that change when you emulsify. Right, it changes certain properties. For example, it creates one homogeneous material from two insoluble materials. And in many cases, they can be quite stable. Like, for example, you have mayonnaise, and that is a material that's incredibly shelf stable. It doesn't separate under normal conditions, and you can keep it in a jar for years, and nothing will happen to it. You will not see that separate because of how stable it is. It doesn't always have to be that stable, but in some cases it can be stable. Other things that you'll notice are the optical properties, how it interacts with light changes. So if you have a vinaigrette or mayonnaise, you'll see that the initial materials, water and oil, are transparent. And in either of those cases, you'll have a lack of transparency in the end from two transparent materials. And that's because of the particle sizes that we're dealing with in this type of suspension, or we can call this it's a colloidal suspension of droplets. In this case, it's a liquid and liquid colloid. So the optical properties change because you have large particles that are suspended with different refractive indices. So when we say large, we would say the diameter is greater than about the wavelength of light over 2. So that is about the scattering limit. When you have any particle below that, you don't have things like certain types of scattering events that occur that would cause light to not pass through it without deflecting somehow. Okay, so that means for blue light, that's about 400 nanometers. So we can say that if anything that any emulsion that, or even colloid, really, that is not optically transparent, meaning it looks white or cloudy or anything like these things, it has particles that are greater than about 200 nanometers in size. You can say that off the bat just by looking at it visually. If particles are suspended that are less than that size, it would still be optically transparent. Large particles, and this is also the fact of the different refractive indices. If they had the same refractive index, you would not get this effect either, because there would be no refraction that occurs between this that would cause scattering. So again, that's just tying back to concepts that you learned in physics too. So in the case of oil and water, they have quite different refractive indices in each other. So both of these things cause interaction with light known as scattering, which has a result of light not passing through in the way that you would expect, right? So it doesn't have a straight path through the material. Okay. So the last thing that is of practical importance, there are other things too, but the other thing that we'll see is very big changes in rheology of the material. So in either of these cases, we'll see an increase in viscosity. So when we think about oil or versus mayonnaise, so oil is like 80 or 90%. Sorry, mayonnaise is 80 or 90% oil, but it behaves much like a solid due to this network of emulsion or particles that exist in it. And as we'll see in a moment, that the particles under certain conditions aren't exactly spherical. They can be much more complicated than that, which can lead to structure. So, and that's the key aspect here, is that these interactions between oil, water, and surfactant can result in complex structures. So there's a whole field of physics and chemistry, material science, chemical engineering that's dedicated to this called complex fluids. So these types of structures are very often seen in biological systems. And also we see them in consumer products. And where a lot of people are trying to use these types of approaches to engineer certain types of solutions. For example, like right now, this is a hot area in the area of robotics. If you think about like how a robot picks something up, say they have like a metal claw or something, they're not really well suited to picking up delicate objects. But if you can make some structure or material that acts more like our human tissue, for example, that's able to sort of squeeze and deform around objects, that would be really beneficial. So to be able to make materials like that that can adapt and deform in these ways requires some complexity, and it's not quite what any specific solid liquid or even many polymers can achieve. So it requires a larger amount of engineering than just taking one material and making it work. Okay, so we can take advantage of these interactions. So I want to show you something. So you can actually make phase diagrams, and I'm going to insert one here. So most of you, certainly all of you chemical engineers, have seen these ternary phase diagrams before. This may look a little different than something you've seen. But I'll walk you through this. So like I said, you can have some very, very complicated structures. So again, let me orient you a little bit in this diagram. So, we have on this line at the bottom, this is just mixtures of water and oil, right? So we have this sort of envelope here, and up here, going up in this diagram is adding additional surfactant. So this line at the left would be just water plus surfactant. On the right, this would be oil plus surfactant. So we can see some obvious things first, right? For oil and water, we just have this disordered medium phase here. So this is where stuff doesn't mix, right? In other words. So even by adding some small amounts of surfactants in that region, you get nothing that is well ordered. You might get a little bit of micelle formation, for example, but generally you're just going to have something that's disordered because and they won't mix. At the other end, it's also quite obvious. Up here at the top, this is too much surfactant, right? It's basically pure surfactant. You add a little bit of oil or water to that as you go down from the top corner, and it's just surfactant powder, basically, that's slightly wet. Right, so it's almost pure surfactant at that point, which are typically either many times powders, sometimes they can be some kind of liquid, but either way, it's so much of it that you can't really make anything out of it. Okay, so the other areas to be interested in perhaps are, when we have these very, we can look at the lines, that's when we have none of something, right? So on this line here, this is just water plus surfactant, and you'll see it goes through some complexity. So at the very bottom, what it doesn't show is you'll just have monolayer formation, right, before you hit the critical micelle concentration. And that will be at or near this corner. Likewise for this. right? Because it's pure oil and you're adding a bit of surfactant, right? And sort of as we described, as you increase the amount of surfactant, you will cross the critical micelle concentration, and you'll get spherical micelles. Again, when you hit the CMC on this side, you'll also get spherical micelles at some concentration. But as you see, you'll get a lot of more complicated stuff as well as you get more complicated. And again, this is all predictable by thermodynamics. It's ways to minimize the free energy of the system. So you can get cylindrical micelles, in some cases lamellar structures where you have layers of oil, water, especially that's in the middle here. So that's a lamellar structure where you basically have layers of oil, water, surfactant that alternate in solution. You can get more complicated structures. In this case, you would have this sort of structure here where you'll have oil inside with water on the outside in the sort of, but with a essentially continuous surfactant layer that extends for very far. So that little cubic block of surfactants isn't just one block, but it'll extend and you can link many of these to each other. And then you can sort of get an idea for why certain things will have different structures. So we can see there's cubic packing here, and we've inverted cubic packing, which would take that same cubic packing structure and essentially turn it inside out, where you would have water on the inside and oil on the outside. So again, you can see there's a bit of symmetry here, not exactly symmetric, but you can get the inverse of most of these structures on each side. And it depends, a lot of this, how this looks depends on the particular surfactant. But the idea here is, the main idea that you want to understand here is that the emulsions will change in geometry to minimize free energy. So this is exactly what's happening in your regular ternary phase diagram that you might have seen for those of you who are chemical engineers in the class that you saw in Chem E 210, right? We have three components, and in some cases you have solubility, in some cases you don't. And you learn in Chem E 381 when you learn about liquid-liquid or liquid-liquid-liquid maybe solutions or instabilities, you learn that the reason for that is that that things become insoluble over certain ranges is because of essentially you're minimizing free energy of the system. So that's all what's happening here. So you can see that the effects of this is interesting because you can get these structures that resemble solids, like with this cubic packing that extends in 3 dimensions. And that's where you can get these solid-like structures that can hold their own shape, right, from 2 liquids, essentially, with a small amount of surfactant, meaning like, less than 1% surfactant in there. So you can, and the surfactant itself can also be liquid. So you can take 3 liquids, mix them together, and make something that has a structure that resembles more of a solid. So as engineers, that is really interesting, right? That we can essentially make squishy solids out of liquids to some extent by taking advantage of the unique properties here and this sort of assembly that can occur somewhat spontaneously. You usually need to agitate this for it to happen. There's an energy barrier for this to happen because they're insoluble, but if you agitate strongly, you can do that. So for any of you who've made something like mayonnaise or even like many cooking sauces, you know that you need to like whisk or heavily agitate these types of things in order for that to work. You cannot make a vinaigrette or a mayonnaise, for example, by just mixing the stuff together and letting it sit, right? But once you agitate it, it forms some kind of quasi-equilibrium state that's difficult to get out of. Okay, so this ties into maybe a few of your projects, maybe especially those of you who are talking about food. and also some other soft materials and stuff like that. Oftentimes these are phenomena that can be exploited for applications like that. Okay, so that should give you a general overview of things. So I just want to make sure that there weren't any questions because we went over this sort of quickly. Will the diagram be different with different components? Will the diagram be different with different components was the question. Could you be more specific, Wyatt?
It's not oil, it's some different kind of insoluble in water.
Yeah, we're using oil sort of as a generic hydrophobic substance, right? So it could be hexane, or it could be something that's essentially non-polar, something that doesn't mix with water, right? So this can happen with wax, for example, or fluorinated hydrocarbons, or various different things. They can be more or less polar. Just the idea is insoluble with water. And the other side doesn't need to be water either. So you can do this with other polar solvents that are not water, like alcohols, or even things like formamide or propylene carbonate, which are polar, but things that are polar organic molecules that behave much like water in a lot of different ways. So as engineers, we have a lot of room to work with. Sometimes we want to avoid any of this happening altogether. Like, for example, people use organic stuff sometimes plus propylene carbonate in making batteries, because propylene carbonate is a common electrolyte for lithium-ion batteries, for example. So engineers at 3M want to avoid making these emulsions inside of there to prevent transport of ions within batteries. So again, often for some applications we want this to happen, some applications we don't. So it's important, no matter where you're working, to understand the basic concept here, that this combination of surfactant plus two things that are insoluble, that essentially where that surfactant can sit at the interface between those, can result in a lot of interesting stuff happening structurally. Okay, but good question. This is very broadly applicable and does not need to apply to just oil and water. That is just conventionally you'll find these called water and oil and water, just because water and oil are sort of the classic examples. Okay, but yeah, good question. Okay, so in terms of emulsions, that is all I wanted to talk about, and I wanted to move on a little bit into a bit of applications. There were some requests to talk about coatings and paints, so I wanted to talk about that a little bit. Let me just pull up my notes here. I can find them. So where is this? I just had it open a second ago. Okay, so let's go over some terminology about paints. Let's talk about paints and coatings. So first, let's talk about broadly coatings. Okay, so coating we can think of as an engineering challenge, right? So if we have some surface, we want to create some coating. And we want this coating to be, uniform, have properties, whatever properties they are that we want. So this can include like color and opacity. This can be things like certain chemical properties that we want. So nowadays, if people build a skyscraper, they have something called a self-cleaning window, and that actually has a very thin coating of particles that take UV light and will cause a photochemical reaction with whatever touches the surface. So it creates a very oxidizing environment, and if it's like some dirt or a little contamination molecule attaches to the surface, it will essentially oxidize it to the point where it can be washed off just with rain instead of building up as grime. So that makes it easy to clean, and you need to get a window washer there less often. So that's, again, another sort of newer generation type coating. So in some cases, this can be like tactile or what we will call tribological properties. So tribology is the study of friction, basically. And there's a bunch of other things that you can imagine. You can think about the electrochemical properties, for example, resistance to corroding. For example, like if you see a car nowadays that's 10 years old, it's very unlikely that you will see big rust spots on it. You know, I'll tell you, when I was in college, most cars that were 10 years old were rusty. You know, that was not that long ago, and that's simply because of advancements in coatings that have developed where nowadays our coatings are so durable that we don't have issues with deterioration of paints like we did even maybe a decade or two ago. So just for reference, I graduated from college in 2006. So not that long ago. Maybe it's long ago for you all. Anyways, so there's a lot of processes that we can coat things with. So if we think about, let's see, where I have those. So there's a lot of technology. So other things that we want this to do is adhere to the substrate. Right, the substrate is whatever we're coating. We want it to cohere, meaning we want it to be cohesive to itself, right? We don't want it to fall apart and get holes, for example, even if it's adhesive to the substrate. Right, so things that we want, for example, if we are coating, say, with a droplet, we put a droplet on a substrate, we want it to spread out. Right, this process is called wetting. We want it to wet the surface. So the thing that we want to maybe avoid is something like this. We have some big droplet we put on there. The other thing, say if that droplet is quite large, that could happen is it forms a bunch of little droplets. That would be called de-wetting. So there's two ways that we can approach this. We can engineer the coating chemistry or the surface chemistry, or both, depending on the application. And we'll talk about both of those. There's a couple really common approaches that are done for both of these. In some cases, for example, modifying the surface, it will not be practical, right? You want to paint your house. Maybe there's a little bit of the stuff you can do. For example, you can put a primer on, and that is something that helps with bonding of paint. But oftentimes you can't do that for whatever reason, something like that. And in some cases, all you can do is modify the surface. You can't really put a coating on it, but you can modify the surface somehow. And we'll talk about ways that that can be done too. If you want to achieve an outcome, you can change the structure of the surface and essentially nothing else. I should add, we can change the surface chemistry or in some cases structure, because that can have the same effect. So I briefly wanted to give you an idea of ways that we can coat. Maybe I'll get more into coding the specifics about paint on Wednesday. So ways to coat stuff. So we can classify this into a few different categories. One we can talk about is vapor deposition. So let me give you a little picture or diagram to help illustrate this. What? Okay, here we go. So this process here is called chemical vapor deposition. So it's a chemical reaction process that happens between a vapor and solid phase. This is called CVD for short. So for example, you can deposit many metal semiconductor materials, metal semiconductor polymers even. This way, if you want to make thin polymer coatings, this works. So let's take the example of silicon. If you want to make a thin layer of silicon. So this is widely used in the semiconductor industry, for example. So you can take silicon, you'd have a precursor. In this case, typical precursor for silicon will be silane, with SiH4. So looking at the periodic table, silane is right below carbon, or silicon is right below carbon. So this is the silicon analog of methane. So the difference here, while they're both gases, silane is pyrophoric, meaning it explodes spontaneously in air. So if you wanted to do this chemistry, it needs to be in an completely air-free chamber, which is done. So usually you'll have some stream of gases that are flowing in, and you will have a surface there, and you will have some diffusion of materials to the surface. On the surface, a chemical reaction occurs. So in the chemical reaction here will be that you go to silicon atoms plus hydrogen, and then you'll get desorption. You'd have adsorption of the silicon to the surface and desorption of that hydrogen byproduct in this case, right? And again, this works for a lot of things. Sometimes the surface needs to be appropriate for this to happen for the thing you want to adsorb. But again, for the purpose of this class, we're going to leave it there. You can do a whole class just on this topic if we wanted to. So another thing, again, I'll show you a diagram to help with this, that is related is we can call this, what we just showed was chemical vapor deposition. And there's a variety of different techniques that we refer to as physical, no, that's not what I want, physical vapor deposition. Let's see if I can get this. Okay, this is a bit smaller than I wanted. Here we go. So there's a few ways you can do physical vapor deposition. The one that I'm showing you here is called sputtering. So in this case, we have some kind of energetic process where we have ionized argon atoms that are accelerated towards this surface. And these argon atoms hit this sputtering target so hard that atoms or clusters of atoms fly off of this sputtering target. And essentially, these atoms go everywhere in this chamber. Usually this will be a very, very low pressure chamber. So typically this will be something like 10 to the minus 9 torr inside of there. Likewise for the one above. So the idea is you take these energetic argon atoms and you give them with enough energy, either by putting them in a plasma source. So you can see here we have a potential applied to one and to the top and bottom. So by applying some kind of oscillating potential, usually apply high frequency potential. It could be low frequency too. So it can be a microwave or radio wave frequency. So in that sort of region. So you apply this potential and that will get these argon atoms that are in this to oscillate rapidly, and they'll hit the surface, they'll knock stuff off, and then it'll essentially snow onto the surface. At that point, you'll have atoms and little clusters of atoms that will hit the surface. So this is, again, a very common way to deposit oxide materials. But the problem is you can see that both of these approaches are confined to sort of a vacuum chamber here. So whatever you want to do needs to be able to fit into a chamber like this. And usually you're limited to something on the order of a meter square or so. It can be bigger than that with some added stuff. And they tend to be batch processes because you need to evacuate these down to low pressure. Okay, so one other technique I want to go over, if I can find this, or two more. This one is pretty straightforward. This is thermal evaporation. Hold on. Copy, paste that. Okay. So you heat stuff up using this power supply. You're making a using essentially resistive heating. So that's how like an incandescent light bulb works. So essentially you put some material in a boat. Usually that boat is made out of tungsten or something that can tolerate really high temperatures. That's the same thing that's in an incandescent light bulb, except this will be a big piece of tungsten that has like a little boat where you can divot where you can put material in. The material in there may melt or sublimate. And because of either the vapor pressure of the material that results, you'll get deposition upwards. The vapor will rise off of this. So you have metal vapor and it deposits onto the substrate. So again, this is a way that you can you have metal condensation or material condensation on the surface from hot vapor. Okay, so usually these temperatures are really hot. So if you ever have the chance to look inside one of these things, they glow bright because of all the heat that's being produced. The tungsten filament usually gets red or yellow, which means that it's approaching temperatures like 2,000, 3,000 degrees Celsius inside of there, but it's fast and efficient. So I'm going to talk about one more vapor deposition technique. By the way, we have all of these things in Sweeney, every one of these in different labs. I have a thermal evaporator actually in my lab. Professor Hillier has some physical vapor deposition tools. I think Professor Wu in our department has a chemical vapor deposition tool. So all these are in our building somewhere. So atomic layer deposition, we have one of these at Iowa State over at the Microelectronics Research Center out on 13th Street. So this is called, also known as ALD. So this is, again, I got a diagram here to help illustrate this. So this is essentially done by a series of chemical reactions at the surface. So this is sort of cool because you have some self-limiting chemical reactions that will allow you to build up a material atomic layer by atomic layer. So you can see that essentially you can flow one precursor in, it'll react with the surface. Then you can flow the second precursor in, and it'll react with that first layer that you made. And you can repeat this over and over and over again and build it up. So I'll give you an example. You can come in with some surface that's hydroxyl terminated. And you can flow in trimethyl aluminum. Aluminum. So that would be AlCH3 3. And what you have is this trimethyl aluminum will react with all those OH bonds. Then you can send this purge that eliminates all the trimethyl aluminum from the system. Then flow in water vapor, which will react with all of the CH3 groups on alumina. And that will turn those CH3 to OH. And you can repeat and repeat and repeat, and you can build up a layer of aluminum dioxide, or sorry, Al2O3. Which is a very valuable material because it is a very good barrier to many materials. Stuff diffuses through it very slowly. So people really like coating things with alumina because it has really great chemical passivation properties. So in the next class, what we'll talk about is some liquid coating technologies, and we'll get into specifics about paint, since that's a very common liquid coating technology. So yeah, the other thing I'm going to do is post some videos just to explain some of this stuff, because these are probably new for a lot of you, but they're widely used in industry. Oftentimes the semiconductor industry, but other industries as well. But these are big employers of chemical engineers and other engineers as well. So it's good for you all to know. So it's 2 o'clock now, so we'll end there, and I'll see you all on Wednesday.